Our topic for today is Z transforms. What are Z transforms? See, you know what are Laplace transforms? You must have studied Laplace transform. If not, you can go to the playlist. You will find a playlist on Laplace transform, and you can see what are Laplace transform, how Laplace transform is done, how inverse Laplace transform is done. So Z transform, when starting Z transform, I expect you should have understanding of Laplace transform and Fourier transform. But it's not that you'll require it in solving the questions. That is not required. You should have a fair concept of Laplace transform and Fourier transform. Now, Laplace transform, as Laplace transform is for continuous time signals, the same is Z transform for discrete time signals. You know there are two types of signals, discrete and continuous. So let this be a continuous signal, which is generally denoted by Ft, and discrete signals we generally denote by Un. So what we do, we apply Laplace transform here, so that the solution of that equation, generally differential equation, becomes easy. And then what we do, we take inverse Laplace transform. Similarly, in case of discrete signals, we apply Z transform, and then what we do, we take inverse of Z transform. So now you understand why we need to study Z transforms, because we have to analyze discrete signals. Now, let me give you the definition. Let's say we have a discrete signal Un, where n is 0, 1, 2, 3 and so on, and definitely n is not equal, less than 0. So it should have values for n greater than or equal to 0, not less than 0. So this is a discrete signal. Then Z transform of Un, it is denoted like this. Z transform of Un, it is written as uz, is actually summation n equal to 0 to infinity. You have Un into Z to the power minus n. This is the definition of Z transform. That Z transform of the signal Un is denoted as uz. It is given as n equal to 0 to infinity summation Un Z to the power minus n, given this infinite series converges. It should converge, then only this is defined. So this is the basic definition. Now let's see some standard results. As if you remember Laplace transform, we know certain standard results like t to the power n and so on. And so we are able to transform a complete differential equation knowing the standard results, and then we take the inverse Laplace transform. Similarly, here also we'll find some standard results that we'll be using in solving differential equations. Okay, so let's see some results. So the first standard result that we'll be seeing, when you can check any book, the first result will be when your Un is actually a to the power n. A is some arbitrary constant, and we have a to the power n as the function. So how to take Z transform of this? So Z transform of this means Z transform of this, what it is, you know, it will be n equal to 0 to infinity a to the power n Z to the power minus n. This is what you will get. So you put 0, this will be 1. Then you put 1, so this will be a by z. Then a by z is square, a square by z is square, a cube by z is z cube, and so on. This is progression where this is your ratio a by z. See, this by this is a by z, this by this is a by z. So you know it is 1 by 1 minus r. So 1 minus 1 by a by z. So what you get? You get z by z minus a. This is the standard result. Now the second important standard result is, which gives you a recursive formula. It is for Z transform of n to the power p. That is n square, or even 1, you can take 1. So Z n to the power p, this will be equal to n equal to 0 to infinity. This is your Un, so this will be n to the power p into Z to the power minus n. Now what you can do, you can take one n out and one z out. So if you take z out, you can take it out of this because we have summation for n only, n is a variable. So I have taken one n out. What you will get? You will get n p minus 1, and we have taken one z out. So this minus 1, so this 1 n minus 1, so this will be, you can write it like this. See it properly. You can write this as this. You can expand this expression like this. Now, second thing, let's see what is the Z transform of n to the power p minus 1. So it will be n equal to 0 to infinity and p minus 1 z minus n, okay, from our basic formula. Now what we do, we take d by dz of this. So d by dz of this will be d by dz of this. Here we have z here only. So what you will get when you will take derivative of this, you will get z minus n minus 1 and minus n you will get out. This is how we do. Let me tell you. See, if we have to take d of this x to the power n, what you get? You get n x n minus 1. So similarly, what you get? You will get 1 minus n out of this. So we will get n equal to 0 to infinity. This is np minus 1. We will get 1 minus n out of this, and then z minus n minus 1. So this will, you can write it like this. Now compare it with this equation. Say this and this. You have one minus sign and you have z here. So that you can write it as this by z. Okay, I'm writing here. See, this thing, this is from here to here. Okay, so we can write this as this equal to minus 1 by z of z to the z n to the power p. Okay, we can write it. So finally what we can do is, here z of n to the power p, this is what we want to find. This will be equal to minus z, see, taking this side, into d by dz of z to the power, sorry, not z to the power, n to the power p minus 1. Okay, so this is a very important result. This way you will know how to find z of n to the power p when one powerless value is known. We will solve many examples and we will understand the importance of this equation. Okay. So we know z of 1, not 1, z of a to the power n is z by z minus a. Secondly, we know z n to the power p is actually minus z d by dz of z of n p minus 1. This we have deduced in our last section. Now let's see, using this we'll find some other results that are also used as standard results. For example, what is the z transform of 1, that is un is 1, then see, this you can write as z of what, a to the power n, that is 1 to the power n, you can write it like this. So it is z by z minus a. So from here what you get? You get z minus 1. Okay, first. Now second, what if you have to find z of n? Then how can you find? Now you can consider it like this, z n to the power p, where p is equal to 1. Okay, so here p is equal to 1. So obviously this will be equal to minus this d by dz of z of what, n. This is p is 1, so np minus 1. So 1 minus 1 is 0. So n to the power 0 is 1. I think you have got. If you couldn't understand, let me give you. This will be equal to n to the power p minus 1. So p is 1 here. So 1 minus 1. So n to the power 0, that is 1. So this is z of 1. And you know what is z of 1? See, z of 1 is this. So this is d by dz of z minus 1. Okay. So what is it? It is minus z here. First is z minus 1, d by dz of z. Then minus z, and here, so it will again be 1, and in the denominator you will have z minus 1 square. So what you get, z cancels, so minus 1, so it is minus minus plus, so what you get is z by z minus 1 square. Okay, clear? So now you understand what is the use of this formula. Now similarly, okay, let me write it here as standard results. Your z of 1 is z by z minus 1, and z of n is z by z minus 1 square. Okay, so these are actually used as standard results. Let's see the third one. Let's see, we want to know z of n square. So this will be minus z and d by dz of what? Z of n to the power, this is 2. So this will be of n, 2 minus 1, 1. Okay, so n, and you know z of n is this. So this is actually d by dz of z by z minus 1 square. You can take differentiation, so that is minus this. This will be z minus 1 square, d, this is 1, then minus z into, this will be, first of all it will be twice z minus 1, and then that will be 1 only, and this is this square of this, so this is z minus 1 to the power 4. Now what is this? See what you will get here. Here you will get z square plus 1 minus 2z, and here you will get minus 2z square, 2z square plus 2z. So 2z cancel. What you get is, see, z square minus, so you get is minus z square plus 1. This is you get, and here you have minus. So what you will get? Minus z square plus 1. So you will get z into z square minus 1. Okay, and here z minus 1 to the power 4. But see, this is what? Z plus 1 into z minus 1. You can write it like this: z plus a square minus b square. So z plus 1 into z minus 1. That z minus 1 will cancel 1 here. So what you will get is z plus 1, and this will cancel 1. So this is q. So this is the z transform of n square. So in this way you can find z of n to the power 3, n to the power 4, n to the power 5, whatever you want. So in sequence, what you should do, you should go for n to the power 3, 4, at least up to n to the power 5. That you can use as standard result, and you should write them in your side of your copy or back of your copy, so that you remember these. Okay. Now let's see some properties of Z transform. Let's see the properties of Z transform. First property is called linearity. Properties of Z transform. First is called linearity. What is it? Let's say our function is un is a of vn plus b of wn minus c of, let's say, xn. These are scalars, arbitrary constants, and these are functions. So this is a combination of these. What will be the Z transform of this function? That we want to know. So let's see. See, Z transform of un will be, you know it very well, n equal to 0 to infinity, un z to the power minus n. So in place of un, you write a vn plus b wn minus c xn. This is your un into z to the power minus n. Or if you take them, rearrange them, what you will get? You will get a n equal to 0 to infinity vn z to the power minus n plus b, again a constant, so it can be taken out, summation n equal to 0 to infinity, it is wn z to the power minus n minus c n equal to 0 to infinity xn z to the power minus n. You see this? Okay. Now, if individually this was for vn, it was, let's say, vz, wn was wz, this was xz. So when you take this, what you get is, this is the z transform of vn, this is z transform of wn, and this is z transform of xn. So I don't have space, so I'm rubbing this. You must have understood this. So what we get is, this is a into z transform of vn plus b into z transform of wn minus c into z transform of xn. Or you can write it as a uz as a of vz plus b of wz minus c of xz. Okay. So this is a linearity property. That is, if you have a linear combination of different discrete functions, what you can do is you can separate them, their transforms, you can add them all, as we do when we have any linear combination. Okay. So this is the first property. Now let's see the second property. this property is also very important. It is called damping rule. Why damping rule? We'll see. So the second property is damping rule. See, we know we have for un the transform is uz. Okay, let's take this. So what if this un is multiplied with a to the power minus n? We have a damping function here. So if we have this function multiplied by this, then this will be n equal to 0 to infinity. This is un a to the power minus n, z to the power minus n. Now you see this, a to the power minus n, z to the power minus n. So what you can do is, you can write it as az to the power minus n. That is to say that z has been replaced by az. So this actually is u of az. Simple. That is, you replace z by az when you have multiplied the original function multiplied by this. Okay. Now similar to this, what if it is multiplied by u to the power plus n, not minus n? See, same way, this will be a to the power n, z to the power minus n, or minus n will be in the denominator. So what you can write as z by a to the power minus n. So what you get is basically u of z by a. Okay. So this is also a very important result, un multiplied by a to the power minus n or un multiplied by a to the power n. So we have seen two very important properties, linearity and damping rule. Now we will solve some questions and understand them. So our first function is n into a to the power n. Now we know what is z of n. This was z by z minus 1 square. Okay, we have seen this. What is n into a to the power n? Now this is your damping one. Okay, so what we do, z of n into a to the power n will be nothing but u of z by a. This you know, and u of z is this one. So what we do, we replace z by a. That is z by a minus z by a minus 1 square. Okay. Now this a, if you take it here, this will be a square up. So what you will get is a z. This is z minus a square. Okay. So the z transform of n a to the power n is az z minus a square. Okay. Similarly, take second case. If we have this n square, then very easy. You must have figured it by now. What is it? For n square, if you remember, this is z into z is z plus 1. So z square plus z, and this is cube. Okay, n square. So when you take a z of this function, n square into a to the power n, what you get is, you will put z by a in place of z. So this is square plus z by a, and this will be z by a minus 1 cube. So if you take this z minus 1, so z minus a cube, and a cube will go here. So what you will get, a cube. So multiplied by a square, it will be a z square plus a square z by, this is z minus a cube. So you get the answer. Okay. Now let's get to our very familiar trigonometric function. We have to find the value of z cos n theta and z of sin n theta. Now looking at this only, you know this and this, you know it very well. E to the power minus I n theta, what do you get? It will be cos n theta minus I sin n theta. Okay, so if we find the z transform of this, then the result will take a real and imaginary part, equate the real and imaginary part. So we'll get z of cos n theta in the real part and z of sin n theta in the imaginary part. Clear? So this is clear to you, then we should start. Z of, let's say we have to find what was I n theta. Okay, this we have to find. Now e to the power I n theta, you can write it like this also. You can write it like e to the power I theta to the power n. Okay, or you can understand it as a to the power n into 1. That is, by damping rule, what we can do, we will find the value of z of 1, and this is your a, So whatever it be, what we'll do, z in place of z, we'll put z by this a. So z, you know what is, for z it is z by z minus 1, this is, you know, but this is a to a is this, so we'll have to put this by e to the power I, sorry, minus, and z by e to the power minus I theta. So this is the result. Now let's expand this so that we can separate the real and imaginary parts. If you take it up, what you'll get this as z by z minus e to the power minus I theta. This is your result. Now what you can do, multiply it by this. Okay, you have multiplied it. So this is what you get is z square minus z e to the power minus I theta. And what is e to the power minus I theta? It is cos theta minus I sin theta. Okay, so again what you can do is z cos theta plus I z sin theta. This is in the numerator, and the denominator, if you square this, you should do this on your own. This is cos theta plus I sin theta. So what you will get is z square minus 2z cos theta plus 1. So this is the real part, this is the imaginary part. So from here what we get is z of cosine theta, the real part, z square minus z cos theta by z square minus 2z cos theta plus 1, and z transform of sin theta, this will be z sin theta by this denominator, z square minus 2z cos theta plus 1. Okay, so we have found the value of the z transform of cosine theta and sin theta. So knowing all the standard results that we have just deduced, let's find the z transform of this discrete function, that is 5n minus 2 sin n pi by 4 plus 5a. So what we do, taking z transform of this, so this will be 5 z transform of n, this will be minus 2 z transform of sin n pi by 4, and then 5 z transform of 5a, these two are constants, so 5a z transform of 1. Now you know what is the z transform of n, it is 5z by z minus 1 square. You know this is minus 2 sin n theta. See, it is z sin theta, so it is z sin theta, that is sin pi by 4. And what is sin pi by 4? It is 1 by root 2, so this will become 1 by root 2 becomes 2 by root 2 becomes root 2z, and then it is z square minus 2z cos theta. Cos pi by 4 is again 1 by root 2, so it will be minus root 2z plus 1, and here what you get is 5a z by z minus 1. So this is the z transform of this function. Okay. Now second, let's say our un is, n plus 1 square. How to find it? Very simple. This is n square plus 2n plus 1, and you know z transform of this and this. So z transform of this function now becomes z transform of n square. What is the z transform of n square? You have seen it. It is z plus 1, that is z square plus z by z minus 1 cube plus 2 into n. N is 2z by z minus 1 square, and this is 1, so this is simply z by z minus 1. Okay, simple. Now, let's see one more example. It was 2, so this is 3. Our function is, let's say, sin 7n plus 5. How to find z transform of this? What we'll do, we'll expand this function. Sin a plus b is sin a cos b, so this will be sin a cos b. Okay, so now what we'll do, we'll take z transform of un. It will be, the constant is cos 5, so cos 5 z transform of sin 7n, and then we have sin 5 z transform of cos 7n. This you know, z sin theta, so this is cos 5 z sin theta. So I'm taking z here, z sine, what is theta means this, see, n theta. So this is sine 7 by z square minus 2z into cos of theta. So cos 7 plus 1. Here what you'll get? You'll get, if you remember it was z square plus z cos theta. So this is sine 5 into z square plus z cos 7 by this z square minus 2z cos 7 plus 1. Okay. Now what you can do is, you can take, you can put them together. So one you'll get out here. So this is z square sine 5. And what about this? See, z cos 5 sine 7. And then again here. So what you get is essentially z of, so it is z of sine 7 cos 5 minus, this is not plus, this is minus, z square minus z cos theta. So minus cos of 7 sine 5, okay, by this one. And you know this is sine A cos B, cos A sine B. So this will be sine A minus B, that is 7 minus 5, 2. So this is essentially z sine 2. And by your denominator is z square minus 2 z cos 7 plus 1. Okay. So this is how we take z transforms. Now let's see our fourth example. What if un, the discrete signal, is e to the power an? What will be the z transform of this? See, it's very simple. Z of e to the power an. This is what we have to compute. This can be written as e to the power a to the power n. And this is 1. So this you can compare it with a to the power n un. That is, you get z by a, that is uz by a. So your a is actually e to the power a. And z1 is what? It is z by z minus 1. So in place of z, we'll write z by e to the power a by z by e to the power a minus 1. So if you take it up, what you get is this. Okay. Let's see what if we have to find for n. Let's say we have to find our un is n e to the power an. Very simple. Z, it is e to the power a to the power n, n. And you know, for zn, you have seen this is z by z minus 1 square. So what you get here is z. In place of z, we'll write e to the power a, then z e to the power a minus 1 square. So square, when you take it to the numerator, what you get is z e to the power a, z minus e to the power a square. Similarly, you can go one step further also. Let's say sixth one, n square. So this will be n square. And what is the value of z n square? It is z into z plus 1, this cube. This you should remember, these are some standard results. So it will be this into z by a plus 1, this cube. So what you get? You get ea cube. So when you take it here, you'll get z ea, because this will be ea square. So z ea into this one, z plus e to the power ea, and this will be cube. Okay. So I think you have got how to proceed, how to take z transforms of different functions. Let's see one or two more examples. So let's see another typical example. If we are given this function is e to the power, or directly I'm writing, if we have to find z of e to the power t sine 2t. Don't get confused. It is as if you have got this en sine 2n. It is very similar to this. And z transform of sine 2n, or let's say theta n, is what? You know, it is z sine theta by z square minus 2z cos theta plus 1. This you know, this is standard result. So this is e to the power n, that is our a is e only. So what we get? Sin theta, and it is z sin theta. So in place of z, what we will write? Z by e, because a to the power n, a, this is this, and about sin theta, theta is 2, so sin 2 by z, that is z by e square minus 2z by e cos 2 plus 1. So e square, if you multiply numerator and denominator by e square, what you will get? You will get z e sin 2. This will be z square, this will be 2z e cos 2 plus e square. Okay, so don't get confused when you see this. Now, what if we have to find the z transform of an impulse function, discrete impulse function? So how do we write impulse function? Del n, which is equal to 1 at n equal to 0, and it is 0 elsewhere where n is not equal to 0. So let this be our 8th example. What if we have to take z transform of this function? So this will be, from our definition, n0 to infinity del n z to the power minus n. Now when you put 0, this will be 1, this will be 1. So at n equal to 0, it will be 1. When n is equal to 1, this is 0, whatever it be. So 0, again 2, 0. So for all other values, it will be 0. So the answer is, what you get is 1. So z transform of impulse function is 1. And let's see one final example before we move to our next topic on z transform. What if we have to take z transform of unit step function? Now it should be z by z minus 1, z of 1. Why? Because we have defined that n, it is defined for n greater than equal to 0 only. So that is actually unit step function only. When we talk of this, it is this only. But what if it is given like this? Let's understand. 1 when n is greater than equal to 0, and 0 when n is less than 0. This is your unit step function. So what is the z transform of unit step function? Let's start from definition. It will be n equal to 0 to infinity un z minus n. Now n equal to 0, 1, 2, 3, everywhere what you will have? You will have 1. This value as 1. For 0 it is 1. So it is 1, then z minus 1, z minus 2, and so on. So this is progression, geometric progression, and the ratio is z to the power minus 1. So it is 1 by 1 minus z minus 1, or you can rearrange it and you will get z by z minus 1, which is for z1. Okay.